Okay. Sorry for the delay, but no, please. Okay. Okay. So, well, welcome, and so there's the second series of lectures of this week. There's Professor Thierry Gallet that you will see last week in the workshop from University of Grenoble, right? And he will talk about viscous vortices, but I actually don't remember now the title of the course. But yes, sorry. Please.
Thank you. So thanks a lot for the invitation. It's a real pleasure to have the opportunity of give this lecture. So the lecture will be completely on the blackboard, but since the projector was installed, I wanted to show you just a quick video. I have nothing on my screen, so can everybody help me running the video because I have nothing here. Yes. I don't see anything. Just run it. Listen. So this is a video from the internet. So this is a numerical simulation of two-dimensional Navier-Stokes equation in a periodic box with periodic boundary conditions. And what I wanted to show you is just to see that after some random motion initially due to complicated initial data, the flow quickly organizes itself as a collection of vortices. Okay. So you have red vortices, which are rotating counterclockwise, and blue vortices, which are rotating clockwise. And you see that they interact. They sometimes merge. I mean, vortices of the same color may merge. Vortices of opposite color do not merge, and so on. So, and you can run this video for a long time. Exactly what you obtain at the end depends exactly what you're simulating. But the message I would like to take from this video is just that, I mean, 2D dynamics in far away from boundaries is all about vortex interactions. I mean, independently of what you start with, you see that the important thing to understand is to understand what are these vortices, how they interact, and if possible, how they merge. So my lecture will be a little bit in this direction. I will have to give you some mathematical results for viscous vortices interacting or in an external environment. So can you just help me switching to this I can flow? Just I have to remove it.
Yeah. So it doesn't switch it off with it.
How do I move the screen up?
So
so much.
yeah. No, ma actor.
Thank you very much. Okay, so thank you. No, there will be no more technical changes. So the plan of my lecture is roughly the following one. So of course, I will start with some gentle introduction. Not necessarily intended for people with a strong background in fluid mechanics. So this should be really easy to follow for everybody. So I will speak about Navier-Stokes equation in the two-dimensional plane up. Then I will speak about some more specialized topics. So I will speak about a viscous vortex in an external. And I shall argue that this is a natural model for interaction of vortices. And then the other lectures will be about, say, well-prepared initial data. And this will be about point vortices as initial data. And if I have time, the last lecture will be about the ill-prepared case. So ill-prepared initial data. this will be about starting with a Gaussian model. All this is supposed to give you some results which go a little bit into explaining what we have seen in the video, but by far not explaining all that we have seen on the video, because we are still, as you will see, in some of a perturbative regime. So let me start with the introduction, and this will be very gentle. Okay. So what about the 2D Navier-Stokes equation? So these are the equations governing viscous fluids. They have been written more or less exactly 2 centuries ago. And in the two-dimensional case, they read as follows: dtu of xt plus u of xt dot gradient u of xt equals to mu Laplacian of u of xt minus gradient of e of xt. So the state variable R could be in a domain of the 2 or 3-dimensional space, but in my lecture, I will comment on this. I will be in the whole plane R2, and the time variable will be, say, non-negative. This is the first equation, and the second equation is that of divergence of u of xt equal to 0. So there are 2 equations. One is sort of the equation of motion. It's obtained from Newton's law of motion. And the second one is a sort of an elliptic equations, which just tells you that the flow is incompressible. So incompressibility is it's a choice. I mean, we could also consider compressible fluid, but I will be happy with incompressible one. So what are the variables? So u of xt, so in my case, it's u1 of xt, u2 of xt is the velocity of the fluid at point x at time. Okay. Okay, so you choose to describe your fluid by the velocity at a given point at a given time. This is not the only possibility. You can also follow the trajectories of fluid particles and trying to describe the velocity or the motion of these fluid particles. This is sort of the Eulerian description. You sit at some point x, and as a function of time, you observe the velocity of the fluid. Okay, so this is the velocity field, which is the main unknown in the Navier-Stokes equation. And now P of xt is the pressure with pressure at point x at time p. And in fact, it's the pressure divided by the density. The fluid has a density, which I don't write because it plays no role, which is supposed to be constant. And so the P here is not really the pressure, it's the pressure divided by the density, but I will call it the pressure. Okay, and there is one physical parameter mu, which is the kinematic viscosity, and which is the viscosity of the fluid divided by the density again, but I will call it the viscosity. This is a physical parameter. So some comments about this parameter. By the way, do you know the value of this parameter? Does anyone know the value of this kinematic viscosity for water at normal temperature? Any idea of what it goes? So I can give it to mu. So mu is 10 to the minus 6 meters squared per second for water at 20 degrees. So you see the value 10 to the minus 6 is pretty small. So it means that if you consider a flow for which the characteristic length is a meter, like in a river, and the characteristic time is a second, so this effect of this viscous term is very, very low. You can say in mu is equal to 0, in which case this is called the Euler equation. So this is, by the way, the Navier-Stokes. Now, of course, this changes depending. I mean, if your characteristic size of your flow is a millimeter, like for the flow of blood in some very thin letter, so this becomes already mu is equal to 1 millimeter square per second. So this changes completely the value, whether this is an important effect or not. So I will keep this parameter because I will play with sending this parameter to 0 for given initial data. By the way, in this setting, you can eliminate this parameter by rescaling of the equation. but then you have to rescale your initial data and so on, so it's not more intuitive. So I choose to keep this parameter in the equation, consider fixed initial data, and then see what happens when this parameter goes to 0. But of course, morally speaking, you can eliminate. Okay? Let me just say one thing, but this is my only comment about other points of view. So you could have you can consider the trajectories of the fluid particle. Even if you have a solution of the Navier-Stokes equation, so you know what the velocity is at each time and at each point, you are not, I mean, you can reconstruct all information about the fluid particles, but for this you have to solve an ODE. So if you solve the ODE, plot of E equals U, F of E, for E less greater than something 0, and X of T0 equals to X0. So you obtain a solution formula of the form X of T equal to some phi of T T0 evaluated at X0. This is just a notation to solve, and this is the flux of the velocity field from initial time T0 to the final time T, okay? And this is a measure preserving diffeomorphism of R, okay? And the fact that it is measure preserving is due to the incompressibility condition. There is this Liouville formula which I use to compute the Jacobian determinant of this quantity. This you learn in classes or throughout differential calculus and so on. So the incompressibility do that the solution map is preserves the volume. Okay. So if you start with some isolate some portion of the fluid here, so on, and you evaluate in time, this will maybe change completely the size, but the volume should be preserved. Not the case, but picture of this different. Okay, so this was very basic about the Navier-Stokes equation. So in fact, I shall not use this equation too much because since I am in a very comfortable setting, two-dimensional case, no boundary, it's much simpler to go to the vorticity formulation. So let me introduce the vorticity formulation. And this is basically the point of view introduced by Helmholtz in the middle of the 19th century. I made some comments about that last week in my talk. Okay, so it's considering here the quantity omega is d1 u2 minus d2 u1. Okay, this is the two-dimensional curl of the velocity. It's interesting to introduce this quantity because I mean this looks a little bit like overdetermined. I mean, you have two quantities, U1 and U2, but they are linked by the divergence-free conditions. And in addition, you have the pressure. Okay. Here on the vorticity formulation, you shall see that everything can be computed in terms of this single scalar function, and this makes the system simpler to study. So to find the equation for the vorticity, you have to take the curl of this equation here. Okay, and everything is, so the curl will kill the pressure. One very great advantage. I mean, this pressure variable is sort of difficult. It's difficult to have an intuitive meaning of what it's doing for the system. So if you can eliminate it, you may be interested in computing the pressure, by the way. I don't criticize the pressure by itself. It's just that playing with having this in the equation and having to determine it using the incompressibility condition is a burden. So if we can eliminate it, it's better. Okay. So the curl will kill the pressure, but it's not clear what it will do on this curve, on this term. So here you have an identity which tells you that u dot graph u in 2D is 1/2 the gradient of u squared plus u per times omega, where u per, it's my notation, is minus u2 and u1. If u is u1, u2, u perpendicular, which is just rotating the velocity field u by 90 degrees in the positive direction, it's minus u2 and u1. Okay. So now if you take the curl of this, curl of u dot grad u. The curl acting on a gradient gives 0, of course. And then you have the curl of this one, and you see that it's d1 u1 omega plus d2 u2 omega. And now using the incompressibility condition, d1 u1 plus d2 u2 is equal to 0, you see that this is the same as u dot grad omega. So the curl of that term is not so complicated anymore. Anyway, so you take the curl of both sides of the equation and you obtain dt omega plus u dot gradient omega is equal to mu Laplacian of omega. This is the equation on which all my lecture will be based. X in R2, T positive. So this is the vorticity equation. Okay. Much simpler, easier to write, pure characters. I mean, this is one of the nicest, cutest equation in fluid mechanics. Of course, if you study Euler, you have no right-hand side here, so it becomes even simpler, but okay. I will consider Navier. Okay. Now, there is a drawback with this equation, of course. You have to pay the bill at some point, that it involves velocity u. It's not a closed equation for omega. So if you want to consider it as a closed equation for omega, you have to express u in terms of omega. Okay? And this is possible, and this is what is called the Biot-Savart law. So Biot-Savart formula. Well, in fact, Biot-Savart are names which are linked to electromagnetism rather, but since there is an analogy with fluid mechanics, the corresponding elliptic equations will bear the same names in fluid mechanics. So what it is, you want to solve the elliptic system divergence of u, so it is d1 u1 plus d2 u2 is equal to 0. This is the incompressibility condition. And curl of u, which is d1 u2 minus d2 u1 is omega, because this is the definition of omega. Okay. And now, how do you do that? Okay. Well, there are several ways, but the usual one is to introduce a stream function. Okay. So you postulate that u is the orthogonal of a gradient of a stream function or some function which I denote by psi. So this is minus d2 psi, d1 psi. So do not worry, it's always possible to find a psi as soon as divergence of u is equal to 0. By the way, if you consider the divergence of this vector field here is automatically 0. So this way of introducing the stream function is a convenient way of incorporating the constraint of incompressibility. Okay. And now so the first equation is immediately satisfied. And what about the second one? So if you take the curl of this, is d1 squared plus d2 squared. So you obtain the Poisson equation, Laplacian of psi is equal to omega. Okay. So the stream function is just the inverse of the Laplacian acting on omega. So now, depending on the geometry of the domain, it's more or less easy to solve this equation, but of course in R2 it's completely trivial. So you have the formula u of x. No, say first psi of x is 1 over 2 pi integral over R2 of logarithm of x minus y omega of y dy. Of course, everything depends on t, but t is a parameter in this elliptic equation, so I can do this operation at frozen time. Also, do not worry, everything I write is completely formal so far, okay? But you have to put assumptions so that everything becomes regular. So for the solution I shall consider in this course, all these formulas make sense. By the way, in 2D, the stream function is not defined uniquely because you cannot, I mean, it will typically grow logarithmically at infinity, so you could add a constant to it. There is no way to choose one particular stream function, but this is absolutely irrelevant for us because what we want is to take the gradient of psi and the orthogonal of the gradient of psi. So u of x is 1 over 2 pi integral over R2 of x minus y per over x minus y modulo square omega at phi dy. And this is the second very fundamental formula, which is the Biot-Savart formula. So here again, I need some assumption on omega so that this integral is meaningful. For instance, omega in L1 intersection with L infinity would be sufficient, but there are some weaker conditions that can be applied too. And in our case, you need some regularity of omega. If omega is just L1, you cannot do that immediately. For the integral, you have problems with it converge. And if omega does not decay at all at infinity, you are in trouble too. But as soon as omega has some regularity and decays at infinity sufficiently fast, there is no problem defining this one. So I will denote in what follow U is PS of omega whenever this formula is valid. So you see that U is a linear function of omega, but it's obviously a non-local function of omega because it's a convolution of omega with some singular integral kernel, not singular in the sense of Calderon-Zygmunt, just 1 over x. So which means that if you practice U is equal to PS of omega, so here I should write PS of omega. And then you see that the nonlinearity is quadratic. It's a quadratic expression in omega, which is, by the way, non-local. So non-locality is a problem. Why is a fundamental physical equation non-local? This is all due to this incompressibility condition, which is here. And this was our choice to go to the limit where the fluid is incompressible. But if you write the full compressible Navier-Stokes equation, there is a finite speed of sound, and you don't have this non-local effect. This is a choice of considering that the speed of sound is infinity. I mean, the incompressible approximation is reasonable in the regime where all your flow that you consider, the speed of all your particles is much smaller than the speed of sound. What is the speed of sound in water? 1,400 meters per second or something like that. So it's absolutely huge, 4 times what it is in the air. So definitely in a normal flow, if you don't consider extreme situations, you are really in the incompressible regime. But the drawback of this is that you obtain an equation which is non-local. Should not be the case. Einstein will not be happy about that, but it is not one of the fundamental equations of physics. It's just a convenient model, which is okay in normal situations. And we have to study it with that in mind. Okay? Okay, so this was about deriving our. So we should all what I'm going to say is based on the study of this equation plus the Biot-Savart law. What is very nice with this equation, so it's minimal in the sense that it considers only one scalar quantity. Yes? Please.
Yes, but if one might also make a formulation without the
Oh yes, you can consider for compressible models, it is also possible to write some form of vorticity. There are some choices, vorticity or curl of U divided by the density or some, yeah, but it's not as clean as what you have here. So it's really the vorticity. The fact here that for incompressible, let me say it like this, for incompressible flows, if you know the vorticity, you know the whole flow, which is no longer the case. So whatever you do, the vorticity will not carry the whole information in the compressible case, whereas it does in the incompressible case. So it's very nice. So it's minimal in the sense that you only solve an equation for one scalar function, which is what it should be in 2D. And also it's very easy to interpret physically. I mean, they'll just tell you that this quantity omega diffuses, the diffusion equation, plus it is advected by a velocity field which is created by omega. So it creates some velocity field and then it's advected by itself. Okay, and this is all about 2D, and everything that is in the movie, it follows from this very simple equation. Okay, maybe in the torus in the case of the movie. Okay, just a comment on the domain. So I go to R2 just by a question of commodity. This equation becomes very cumbersome when you have boundaries, if you put no slip boundary conditions, because it's very difficult to write boundary conditions for omega. You can, but they are not very easy to handle. So here, being in a domain without boundary is a great advantage for using the vorticity formulation. Now, I consider R2 rather than the torus because the torus is just for numerical simulation, but has no physical reality. So R2 also is a little bit big, but I mean, if you consider vortices, the motion of vortices far away from any boundaries, certainly they are described reasonably by this equation. Okay, now do we know solutions? Well, a lot of solutions to the equation. In particular, there is a class of solution which is the case of radially symmetric vortices. Not in the introduction where everything is well known, but let's continue. What about radially symmetric vortices? A class of particular solutions of Navier-Stokes equation. So I will introduce some polar coordinates because polar coordinates without much originality. I will write R of theta and R in theta. I will also introduce some unit vectors, ER, which is x divided by modulus of x, which is cos theta and theta, and the other unit vector and V, which is in fact ER orthogonal, which is x per modulus of x, which is of course minus sine theta plus sine of theta. Now I suppose I take the vorticity of a particular form. I suppose that omega is a function of modulus of x times that's it. Sorry for not being very careful writing the same later for omega and the radial profile. So suppose that you have that. What can you deduce? So if you solve the Poisson equation, so everybody knows that the Laplacian operator is invariant on the rotation. Okay, so if omega is radially symmetric, definitely psi is also radially symmetric and can be seen really from the formula. So this is true that psi is also psi modulus of x. Okay, and then if you make a calculation, you will find that, okay, when you differentiate, so it is u is psi prime of modulus of x times e theta, and let me denote this by v of x times e theta. Okay, so it means that the velocity field is a radial function of r multiplied by e theta, which means that you can draw the streamlines. The streamlines are the integral curves of the velocity vector. So what are the streamlines of this vector here? These are just concentric circles centered at the origin, which really the intuitive notion of we have a vortex. Okay? Like that. So we have the free particles rotate in some direction, and the speed, depending on the radius, is governed by this equation. Now you compute omega, which is the curl of Q, and by taking the formula for differentiating in polar coordinates, blah, 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 what you obtain is that it's 1 over r p prime, no, 1 over r times r p prime. Okay, evaluated at modulus of x. So this means that you can find this function. For the moment, I didn't say what psi is nor p, but now I can solve this equation for v in terms of omega, and then you obtain the formula that v of r is equal to 1 over r integral from 0 to r of omega of s times s ds. Okay. So if you have a radially symmetric vortex given by a vorticity profile omega of r, then here the way you find the velocity. The velocity is v of x times theta, which I wrote here, and the v, the profile v, the velocity profile is found by this equation. Well, you can also plug into the general formula for Biot-Savart law, but then good luck to do the calculation. It's completely ridiculous. So the way, the radially symmetric case, the correct way to use this formula.
By the way, you can also be interested in that case in the pressure. I completely forgot the pressure because I eliminated by going to the vorticity. But suppose you are interested in the pressure, you can compute it. Of course, it's radially symmetric in this situation. You have P prime of R is equal to -1 over R, V of R squared. It's not very surprising to find V squared divided by the radius, right? The acceleration in when you do a circular motion. So this tells you that P is a decreasing function of the radius. P prime, yes, which means I have a problem here. I'm going to observe something which is completely wrong. I have a problem. I wanted to tell you, no, see prime is that inside a vortex, you always have yes, you always have a depression. So the gradient of the pressure should go towards the center of the vortex. No, sorry, I was confused for a moment. So when you have no external force or whatever, inside a vortex, you always have a depression and not a region of high pressure. And this you see by this. Okay, now the fundamental observation I wanted to make in the radially symmetric case is that the nonlinearity in the vorticity equation just disappears. Okay. So a completely elementary but fundamental remark for what we do. The following remark. In the radially symmetric case, if you take u dot grad omega, so it's very easy. You take the expression for u over there, v times e theta, so it gives you 1 over r times e v of r times e theta omega. This is equal to 0 because omega does not depend on theta. It's a radially symmetric function. So the nonlinearity vanishes identically for radially symmetric vorticity. I mean, it's not surprising because I draw the picture of the straight lines. So this means that the radially symmetric distribution of vorticity is affected by a vector field like that. It's like rotating something which is radially symmetric. It has absolutely no effect. Okay. So and this implies that the equation for omega reduces to the heat equation. So this is something that you have to keep in mind. For radially symmetric vorticities, the 2D Navier-Stokes equation reduces to the heat equation. So we know the solution explicitly. There is an integral kernel. We know intuitively what the solution is doing. So I mean, these are maybe not the most interesting solutions of 2D Navier-Stokes, but they exist and they certainly describe individually the vortices that we have seen in the video. Each kind of this vortex, if you consider it completely disconnected from the environment, will converge to something radially symmetric. If they are not radially symmetric, it's because they are interacting with other vortices. Okay? And this is what we want to consider. But these radially symmetric solutions are really the building blocks for studying the vortices, and so we should not underestimate them. So examples. Example 1, if you open books by fluid mechanics, you find many examples of radially symmetric vortices with names. And the first one is Rankine vortex. Rankine's vortex. So you fix some parameter capital R, and you take omega of small r being gamma, and you fix also some parameter gamma, which will be the intensity of the vortex, gamma over pi r squared times the indicator function of 0r. Okay, so you suppose that the vorticity is just the indicator up to a multiple, the indicatrix function of some radially symmetric disk, some disk. Okay, so the vorticity is constant inside, 0 outside. So this is Rankine vortex, and if you compute the corresponding profile, the velocity profile, you find gamma over 2 pi r times small r over capital R if r is less than capital R, and the converse, capital R over small r
if R greater than capital R. Which means that this vortex is very easily described. Inside the disk, this is rigid rotation. The angular speed is linear with the distance to the origin. So it just means that the disk is rotating like a solid body, okay? And outside is irrotational flow. Because the velocity, the vorticity is zero, and you match them at the boundary in such a way that the speed is continuous. So this is a caricature of a vortex, but it's widely used in the physical literature because it has a simple analytic form, okay? So inside, you have a disk of radius r. Inside of it, you have rigid rotation of the fluid particles. Outside of it, you just have irrotational flow, which means that the velocity decays like 1 over the distance to the origin. So this is Rankine's vortex. Not very realistic. Now it's a realistic example. Lamb-Rosane vortex. So you have the same parameter. And now you assume that the distribution of vorticity inside the vortex is Gaussian. So gamma over 4 pi. It is a factor that I want to put, r square. I have to put this r square e to the minus x square over 4r square. So this is a Gaussian with standard mean deviation proportional to r. So the size of the vortex is again r, but of course the support of vorticity goes to infinity because it's Gaussian. And the corresponding velocity field is interesting. V of r is gamma over 2 pi small r, 1 minus e to the minus x square over 4 capital R. So we have here data for the Rankine vortex and here for the Lamb-Rosane vortex. So this one is very important because this is the one produced by the heat equation starting from Dirac mass as initial data. So a point vortex, let me just mention this to conclude. Well, this was not the correct board, I should be erased, sorry. So it's too late. This was not. I should get accustomed to the 6th before. It will come before the end of it. So you have a singular limit, which is a point vortex. So a point vortex can be obtained from the preceding examples by taking gamma in R fixed and by sending the size of the vortex to 0. So you suppose that the vortex is more and more concentrated. So you do that in both equations and you find the same thing. You find that omega gamma times the Dirac mass of the origin, say, and that V of R is gamma over 2 pi R. In both formula you obtain, if I am correct, it will give the same expression. So this is the velocity field of a point vortex. For a point vortex, the velocity decreases like 1 over the distance to the origin, so it's singular at the origin. Yes. Oh, these are okay. For Navier-Stokes equation, we'll speak about. For the moment, these are just time independent. Okay. Now we shall see that, for instance, the Gaussian vortex, if you let R evolve with T like R squared is equal to nu T, is a purely classical solution of the heat equation and therefore also of the vorticity equation. So you will have a real solution looking like that. But for the moment, it's just something fixed, independent of time. It is, you could tell that you could take them as initial data for Euler or Navier-Stokes equation, and they will give rise to absolutely smooth solution of the equation. Okay, now let me come. So this was just some basic material. So now let me come to interaction of vortices. So this will be a little bit vague, but I have to come to this point.
So what did we see in the video? Okay, in the video we had some two-dimensional domain. Here I consider the whole space, X1 and 2, and after some time, the vorticity was not at all spread uniformly on the domain. It was concentrated in some elliptical-like regions, circular ones, which will move with some velocity. They were rotating in one sense or one other. So this is roughly what we have seen in the video. I wanted to show you the video just so that you cannot believe that you don't have to believe me that this is what you see in two-dimensional fluid. Okay. And now we'd like to try to describe a solution where the vorticity is a superposition of a finite number of relatively well separated vortices. Okay. So in that case, it's very okay. This will be a solution of the two-dimensional vorticity equation. So what should we do? It's very obvious. You should consider omega of xt as the sum of I from 1 to n of some omega I of xt, with the idea that this omega I, we put labels here 1, 2, 3, capital N. This will be this vortex blob that we have seen in the video. Okay? So let's look for a decomposition of omega as a sum of omega I. Looks pretty relevant. If you do that, the velocity field u of xt can be decomposed in a natural way as sum from 1 to n of ui of xt. If you define ui is equal to Biot-Savart law of omega I. Of course, the Biot-Savart law is linear, so if I have a decomposition of omega into a sum of blobs, I can associate a velocity field to each blob, and then when I sum of this velocity field, I recover the whole velocity field. Okay, so far so good. The only problem is that this decomposition is completely non-unique. I start with one function of x, d, and then I should introduce capital N functions. So of course, there is not a unique way of doing that, okay? So if they are really separated, they are compactly supported or something like that, then you see, okay, I know what to take as omega I. But they will not be compactly supported. I'm solving some parabolic equations, so of course there will be some overlap. So there is not a unique decomposition. So you have to decide how we decompose this. So, and this is done by the following way, which is very simple, but you have to understand it at first place, is that we postulate, this is our choice, that omega I solves the equation dt omega I, so dt omega I plus u dot grad omega I, not different, it is u dot grad omega I is equal to mu Laplacian of omega I for I from 1 capital N. So this is not completely obvious. What do? I consider, okay, maybe the easiest way to explain that is to say the following thing. At initial time, t is equal to 0, when you start studying the system, you see that your vorticity is a sum of well-defined vortices. So you label these vortices by omega 1 to omega n, the best you can. And then you solve Navier-Stokes equation, starting with this initial data, and you denote by u the full velocity field. The velocity field produced by everybody. Now, if u is given, this is a linear equation for omega I. Okay, so if you have a decomposition initially, this you can solve for each omega I. And when you have computed this omega I, when you make the sum, you will recover the full omega. So we decide that all of these vortices are advected not only by the velocity field, which is produced by the omega I, but by the full velocity field. And except for the decomposition initial time, this is now a unique way of decomposing the solution. So we decompose at initial time. Okay, suppose that at initial time, for instance, we have point vortices, so we know how to decompose. And then you solve
but each omega I is advected by the full velocity. So they solve a linear equation if you take into granted that the velocity field is known. Okay, so this is what we do. Now, of course,
Is it correct to think that as soon as they have a bit of viscosity, then for long times they have to converge to a steady state?
ST goes to plus infinity. Okay, so let me make a comment later. I didn't, for the moment, consider at all this question here, but everything is known for, okay. The long time behavior, let me say that if you take omega as initial data, the long time behavior of the 2D vorticity equation is the same as the long time behavior of that equation. So yes, that's true. But this is far from the consideration I'm doing here. So now, remark. Okay, this U is a sum of Ui, and U's I are the PS of omega I. Okay, so you can write U equal to Ui plus Fi, where you define Fi is equal to the sum of J different from I of Uj. This is also the sum of the J different from I of the Biot-Savart law applied to omega J. So artificially, I can write this equation as U in this equation as Ui, which is produced by the omega I, and Fi, which is the result of the velocity field produced by all the other vortices. So this is the equation star. So equivalently, I can write my equation star in the form dt omega I plus Ui plus Fi dot I omega I is equal to nu Laplacian of omega I. The second equation is exactly the same. I'm just rephrasing things. This is my equation. Adam star. And here the meaning is of this equation is I consider my one vortex block. So now I don't consider the whole picture at the same time. I'm concentrating on one of these vortices, the vortex omega I, and I see that rigorously, the Navier-Stokes equation plus my choice of defining this tells me that this equation, this omega I, evolves according to the diffusion plus the advection by, this is the self-interaction, Ui impacting on omega I. This is what would happen if the vortex was completely isolated from the rest, plus Fi, which is the effect of all the other vortices. So here, I have to distinguish between self-interaction. This is interaction with, say, the external world from the point of view of my vortex. This is the rest. Okay. And in fact, what I shall do in these lectures is consider exactly this equation. Okay, I shall consider an equation. I consider that Fi is given. So now I concentrate on one vortex and I get rid of all the other ones. They will just produce a velocity field. This velocity field will satisfy some estimates. I will consider it in my lecture as being given. And I will consider the equation for one vortex in an external flow, which could be produced, for instance, by the other vortices in the interaction process. And I claim that this is the simplest model we can study to understand what happens to a vortex in an interacting environment. You can write, of course, interacting configuration like that, but it's even simpler to consider a single vortex and assume that F is given. Okay? And if you use only some general bounds on F, you obtain results which are completely tell you what will happen for interacting vortices. So this is basically the philosophy of what I do in the lectures, which avoids considering some of configurations, just one single vortex. I want to see what happens if I put an external field, taking in mind that what I have in mind is this interacting picture. So before, this is what I shall do starting from chapter 2, but let me finish this introduction by a little bit of phenomenology of vortex interactions so that we agree of which kind of phenomena we want to study. Okay. This is all well known.
find this in physics books. So phenomenology, G of vortex interaction. What is known, what is expected, what can we do? Okay. So for the moment, okay, I will assume that the vortices described by omega I and so on have a definite sign, or at least that the integral of omega I is non-zero. The idea is that I will separate blue vortices and red vortices that we have seen in the videos, and clearly in these vortices, there is a definite sign, or at least a non-zero integral. So assume that omega I has a definite sign, so that the quantity gamma I, which I denote as the integral over R2 of omega I x, is non-zero. So important remark, this quantity is preserved under the evolution because the equation for omega I, say this one, is the diffusion equation plus the advection by a divergence-free velocity field, and this doesn't change the integral. I could write this u dot grad omega I as divergence of u omega I, so the integral is certainly not changed. I'm still at formal level. I'm doing formal calculation, but this is some, okay? So these parameters gamma I will be non-zero and will remain the same. So I fix them initially by choosing my initial data, and then each vortex has a well-defined circulation for the rest of its life. Okay. By the way, this means, remark, this implies that UI is not in L2. I didn't speak about L2 of vorticity or velocity, but L2 of velocity field is the energy space. Finite energy solutions have a velocity field in L2. This is not the case of each of these UI. Maybe the sum of U has a finite energy, but if the vortex has a non-zero circulation, the corresponding field cannot be in L2. So this is supposed to be lectured. I should be exercises or exercise for tomorrow, especially for the young graduate student. If you take U, a velocity field in R2, okay, just L2, you assume that omega, which is D1 U2 minus D2 U1, is in L1 of R2, which is, of course, it needs not be, but I mean, for a velocity field in L2, this is an assumption. You take the curve, should be a distribution, but you suppose that it's an L1 function. This assumption together imply that integral over R2 omega Ex is equal to 0. So as soon as you have a finite energy velocity field, the corresponding omega has 0. So if you steer a two-dimensional fluid with your spoon, you create exactly the same amount of positive and negative vorticity. Otherwise, you need to put infinite energy to your. This is due to slow decay at infinity. The problem is slow decay at infinity. We have seen that the velocity field decays like 1 over the distance at infinity. This is the case in this example, and this is just not in L2. Okay? But of course, in reality, you produce always the same quantity of positive and negative vorticities, so you don't have this problem. Good. So each of these vortex has infinite energy, but maybe the sum has finite energy, and so on. So now, let me consider another quantity which is very interesting, which is the center of vorticity. Okay. So define the center of vorticity of the vortex omega r. So if the vortices are well localized, we would like to say that they are centered at some point. So we need a definition of what could be the center of the vortex. There are at least 3 different definitions in the literature of how do you define the center of a viscous vortex. but maybe the simplest one is the center of vorticity. We define xi of t as being 1 over gamma I integral over R2 of x omega I of xt dx. You take omega I, it has a definite sign you consider as a distribution of mass, and you average the position over this distribution of mass, and this gives you the center of what is called the center of vorticity. Okay, so this one is not a conserved quantity. It is for the full Navier-Stokes equation, but when you have an external field like this I, it's not, because there is a calculation which I'll do later, xi prime of t, but let me just use it for the moment, is 1 over gamma I. Again, it's formal, but can be justified. Is integral of fi of xt omega I of xt dx. So the velocity of this center of vorticity is just the average of the external velocity acting on omega I. Okay? So the self-interaction doesn't come into the picture. The self-interaction does not contribute to the motion of the center of vorticity. It's only the exterior one. Particularly, if you don't have any external field, this is 0. The center of vorticity is conserved. Okay? Okay, so that's a very nice formula. And now what do you do with that? Let's consider the case, the limiting case where the vortices becomes really very small compared to their distance. So the limit where they converge to sort of point vortices, okay? So consider the formal limit where omega I of xt converges with gamma I delta of x minus xi of t. So I consider formally, I take the limit where they are so concentrated that for all practical purpose, I can consider them as Dirac masses of circulation gamma I, of intensity gamma I, centered at the point xi of t. So then xj of t in this limit, xj prime of t, xi prime of t, sorry. Well, then if omega is a gamma at the Dirac mass, it's easy to compute this integral. This just tells you f of xi of t and t, right? I don't need any, I don't have to compute the integral because it's a Dirac mass. So it's just evaluating at x is equal to xi of t and this one. So the center of vorticity should just be affected by fi. What else can we do? But now the same limit, this fi, I recall, was the sum of the uj. The uj was ds of omega j. But omega j are no Dirac masses. And for Dirac masses, we know exactly what the velocity field is. This is this limit that I mentioned here. Okay, so this gives you the sum over j different from I, the same sum as here, gamma j over 2 pi, xi of t minus xj of t perpendicular over xi of t minus xj of t modulo squared. And this is a system of ODEs for the position of these point vortices, and this is called the point vortex system. We'll put a label which is point vortex. So this very, very known system of ODEs was considered a little bit in the paper by Helmholtz in 1858. It was certainly studied in the book by Kirchhoff of 1876. And the first mathematical study of this system is the PhD thesis of Walter Gröbli at the University of Zurich in 1977. And then there is a book by Poincaré and many, many studies. Okay, it's really, if you pile up all the papers that have been produced in that system, you don't reach the top. Okay, so it's a little bit like celestial mechanics, but celestial mechanics for fluids. It's a little bit simpler. It's two-dimensional. A lot of things is known. And this describes a motion of the center of vorticities, which is to very good approximation what you see on the video. On the video, you have this red and blue vortices moving. If you compute the velocity field using this approximation, you are already very close. Okay? So when the vortices are very widely separated, the motion is well described by this. This is just a statement in the air.
But we shall see is the rigorous statements that will justify this. This can be justified rigorously in some limits for the Navier-Stokes equation. Okay, so this will be part of the lectures, is to see what can be said about this system. Yes?
So what they know from the right equation that the finite equation of prediction that showed us just two opposites with different signs. So can you see these from this equation?
This is okay. This from this equation, certainly no way, because this is completely dependent that you are in the torus. So this the long time behavior, I keep getting questions for long time behavior, which was not my intention. This is really, you see really the size of the domain. What I say here, for instance, this is relatively robust. In the torus, it's just that the velocity field, the Biot-Savart law, is a little bit different because each vortex is in fact an infinite number of vortices by mirror. But except from that, the kernel is a little bit, you have to change a little bit the dependence, but this is more or less the same. For long time behavior, I mean, in the torus, everything converges exponentially to 0. In the torus, the integral of omega should be 0, because otherwise the velocity field is not periodic. If you assume that not only omega is periodic, but the velocity field is periodic, means the omega should have the 0 integral. And then it's known that you converge exponentially to 0 at the end. But in a regime where all the interesting turbulence and behavior has disappeared. Okay. So the interesting dynamics is not in the long-time asymptotics. The long-time asymptotics can be computed in most of the system. So in the whole plane, it's just a single Ozane vortex, the circulation of which is the total circulation of the system. This is a result by Jean Wayne and me 20 years ago. And in the torus, it's known to be exponentially convergent to 0. All the interesting dynamics is before that. And it's not completely understood, and we try to understand it. So now the simulation, of course, will show this dipole, and this is expected to be the behavior, but there is no proof so far that we really shows this dipole. Yes?
There is stability of when you take initial conditions which converge to
Okay. I'll discuss this a little bit later, so let me postpone the answer to this question. I just said that this problem was solved in Italy. This is the long time work of Marchioro and Pulvirenti, showing in which, under which assumptions, if you start with initial data which are well concentrated, you stay well concentrated, and you evolve according to this system. This is the work since the 80s of Marchioro and Pulvirenti, which I shall mention a little bit later. But yes, there are thanks to Turkington and Marchioro and Pulvirenti, especially, we know a lot about in which sense this approximates the original physical configuration. I should take one type of results, and the other are due to other groups. Okay, so this is what I wanted to mention rapidly. So this is okay. This is the point vortex system. Now, to end with the phenomenology, what is known beyond the point vortex system? We consider a very simple situation. Justifying the point vortex system is already a very good point, but my lecture will be rather about questions which are beyond the point vortex systems. So beyond what you see the point vortex system, let me take two examples. Example one, let's take a vortex dipole. For a vortex dipole will be, for instance, a vortex with circulation plus gamma, and here minus gamma. Okay. Well, I assume here that gamma is positive, otherwise I will not write it in this way. So a positive vortex and a negative vortex. In that case, if you solve the point vortex system, well, it's not very difficult to see that this is uniform translation with a constant speed in the directions which is perpendicular to the segment that joins the center of the vortices, okay? And the vortex, the speed can be computed is gamma over 2 pi times the distance. Okay? So if the distance here is b, this is the vortex speed, which is gamma over 2 pi d. This is the prediction of the point vortex system. If you have two vortices of opposite circulations,
they will just move with constant speed. And you see a little bit of that in the video. Sometimes, okay, they have not exactly the same circulation, but you see a blue and a red that do a little trip together, and this is this one. But in fact, if you compute now with a final, this is like point vortices. Point vortices are infinitely small compared to the distance. They are not in reality. So you see some deformation. They get deformed due to mutual interactions, and we can compute how they are deformed. And I can show you they are deformed in that way. The vortex lines become elliptical, a bit like that. And they get elongated in the direction of propagation. So this continues to propagate more or less with the same speed. But this is what you see both on the video and if you make a careful numerical simulation. So this can be computed. They deform itself in such a way that the external, if you consider one of these vortex, the action of the external field is exactly cancelled by the self-interaction except for a translation. So you can compute this. It's not trivial to see that it works. But this, I shall also do this calculation in the lecture. Now, example 2, in the same category, it is the co-rotating vortex pair. Okay. In that case, this is now plus gamma and plus gamma. In which sense? So two equal vortices, okay? So in that case, you have uniform rotation around the common center. Take the center of mass of the system, and you have uniform rotation at some angular speed, which can be computed also in terms of gamma at the distance, okay? So we have omega here, omega, and I suppose it's gamma over pi. This is the angular rotation speed and so on. Okay, so this you can compute. This is solution of the point vortex system. So again, on the video, you see that two red vortices have a tendency of rotating around each other. Now, beyond the point vortex system, you will see how they get deformed. And once again, they are deformed in such a way. Not the other way around. This is what you obtain. So it's not the same as in, they do not, I mean, okay, so, yeah, it's the way the vortices are getting lost. This again can be computed by an expansion that is necessary to formulate rigorous results on this problem. Yes.
But this, so when you say they are deformed, you mean by the fact of the interaction, so the fact that the initial support is not concentrated, which means is this Euler or Navier-Stokes?
Well, I mean, let's say you start with this at equal to 0, Navier-Stokes produces that. If you start with Euler, you are interested in Euler? Yeah. If you start with radially symmetric vortices in Euler like that, they will undergo some fast oscillations, and they will settle down in some metastable equilibrium state, which looks like that. If they are, I mean, if you are interested, if you force me to speak about Euler, which was not my intention, there exist exact traveling wave solutions of Euler. So there are solutions which are constant, which are stationary in a moving frame, so they have compact support, and if you look at how they look like, their streamlines are deformed exactly in that way. In the same way, there are exact solution of Euler, which correspond to a rotating pair, so they are stationary in a uniformly rotating frame. This has been proved also, and once again, so this is both true for Euler and Navier-Stokes. It's a general fact. And the question is, how do you compute that? How do you use that? Maybe a last comment to finish this long introduction. What is the long people seems to be interested about the long time dynamics. What happens to a vortex dipole? What happens to a co-rotating vortex pair? Completely different states. For the vortex, the vortex pair, they are rotating around each other, but the vortices become larger and larger diffusion. And at some point, when the typical size divided by the distance reach the value of 0.44, so can be why, they start merging. And you see that in the video, they have a violent merging phenomenon, which was, there were pictures about that in the talk by Michele Dolce last week. And this is nonlinear process, very complicated. We have absolutely no rigorous mathematical description of that. So we are not able to follow the solution to that. For the vortex dipole, it's much more gentle. The vortices increase, so they get closer together. They start a little bit mixing, but nothing like a violent merging phenomenon. The vortex slows down, and at some point, it's they mix together and they go to zero on the same thing. So it's very different for the vortex dipole and the covalent vortex pair, but I have absolutely no mathematical results to present in this direction. Okay. Yes.
So basically, so they slow down and then they basically get closer.
Yes.
So this first order law basically completely fails because the velocity in the vortex dipole is inversely proportional.
Oh yes, this is a regime. This is a regime which requires a separation. It's completely wrong.
Exactly.
Yeah, no, the point vortex approximation breaks down before they start really mixing. That's true. Okay. Do I still have 10 minutes or something like that?
Yeah.
Or? Yes.
Instead of the point vortex, we start with the two range vortex.
Yes.
Then we start do we get the same information of the ellipses?
Yes, but not immediately. Immediately, there is a boundary layer in time. Because it's like, this is exactly the distinction between my chapter 3 and 4. Well-prepared initial data or ill-prepared initial data. Well-prepared initial data for Navier-Stokes, I will argue, we start with Dirac massive. So they have no problem choosing what they are, and they grow immediately in the interacting mode where the streamlines are deformed like that. Good, no problem. If you start with something else, say a Rankine vortex or a Lamb-Bosane vortex and so on, radially symmetric, and you turn on the interaction brutally at initial time, they will have to, there is a transient process which is a little bit more difficult to capture, but we have some result about that. And they settle into an equation, interacting state, and let it evolve normally. Okay. So what I want to describe here is the well-prepared case where you start from a Dirac mass, and then if I have time to tell you what the little that is known in the more general case. But the canonical problem to study is really when you start with a Dirac mass for Navier-Stokes. But this raises some difficulties. Is it possible? Do we know that the solution exists and things like that? Okay.
The size of the size of the
Yes, yeah, sure. Okay, that's it. So in the last 10 minutes, let me just start with introducing the problem we'll study in more detail in the further lecture. So this is already my chapter 2. So chapter 2, a viscous vortex in an external fluid. So for the moment, from now on, I will consider only this model, and I think I motivated the study of this model. So my equation is now PPU of xt plus U of xt plus F of xt dot grad omega of xt is equal to nu Laplacian of omega of xt. So x R, T will be positive, and this is called the vorticity equation with the term F, so I call it Df. So this is the equation I shall consider, with, of course, U would be the pure Savart of omega. So U is the velocity field produced by omega, and F is now given. F is a given external field. I will only make some general assumptions about smoothness on F and things like that, but dt omega, oh yes, oh yes, oh yes. This would be violent liters on time issue. Thank you so much. And inconsistent in dimensions. Oh yeah, I'm getting tired of it. So it's nearly the end. So I will give only some general assumptions on F. So I assume that F is divergence free. This is essential. Otherwise, doesn't work. So divergence of F is 0. And F, I will suppose that it's smooth. The second assumption can be relaxed. It's not always completely true in the situation I have in mind, but this simplifies the analysis and does not distort the picture. So I have that RF, for instance, is continuous and C infinity bounded from R2 times some time interval 0 capital T, this value in R2. This can be relaxed. I mean, this is maybe a little bit too much asking, but anyway, doesn't change that. Okay. So this is in some sense, I did use this model as a particular case of Navier-Stokes, but of course, as it is stated, it's an extension of Navier-Stokes, because of course, if I put F is equal to 0 in the equation, I'm back to the vorticity equation. Of course, F identically 0, then you are back to the vorticity equation. So it's like an extension of Navier-Stokes. It's like Navier-Stokes plus an external field, but of course we have in mind that we will study some simple solution of this equation, which correspond typically to a single vortex. The other ones are contained in this F, which I'm given. So now, yes, sorry.
When you have the velocity related by velocity, the curve of the velocity field is the velocity.
Yes.
So this F is the external field, then we use that curve F equals 0 since it's related by velocity that does not touch.
Very good questions. I mean, at the moment, I do not assume that the curl of F is 0 on the support of the omega I will consider. But this will change a little bit some details. So sometimes it's good to take in mind that, of course, in the situation I have presented, it's not unrealistic to suppose that curl of F is equal to 0. So F could be a potential flow, and this could be an interesting situation to consider. Okay. In fact, there is also possible to have, I mean, you could have also a single vortex in a potential flow, which is not produced by other vortices, but by an inflow condition at infinity, like sending a flow at infinity. And therefore, in that case also, curl of F could be 0. So the results I shall present do not require curl of F to be 0. So we don't need this assumption, but it's realistic to have that in mind. This could be, this simplifies a little bit here and there, and I will mention that when you come to the point. So the question now, we shall start some analysis. So what do we know about this equation? So typically, compared to the vorticity equation, we are adding a lower order term. I mean, this is just a single derivative where we have two derivatives here, and F is given is smooth, not like the nonlinearity. So basically, all what we know about 2D Navier-Stokes in terms of Cauchy problem and things like that is also true for this equation under these very comfortable assumptions. It's just a question of modifying a little bit the proof. So for instance, you have proposition 1. The Cauchy problem for this vorticity equation with additional term F is globally well posed. in the critical space L1 of R. So here I make some allusions to the Cauchy problem for the usual vorticity equation. So if you, there are many spaces in which it's known to be globally well posed, but one of the simplest one, which is invariant under the rescaling of the equation, is L1. If you take omega to be integrable, we know that we have a unique global solution, okay? So this is still true here. The proof is not written formally anywhere, so as far as I know, but it's just a simple modification of the proof for the vorticity equation. So let me just mention what this means. We consider the integral equation. This will be the integral equation. So you write an integral equation corresponding to this one. So omega of t is equal to s of mu t omega 0 minus integral from 0 to t s of mu p minus s divergence of u of s plus f of s omega of s. Yes, I will not insist too much on that. So if you know what I'm writing, it's okay. S of t is the Hilson niveau with R2, which has very nice solution. And you try to make a fixed point argument to solve this equation, okay? By a fixed point argument in some space. So we consider a mild solution. Omega, and this will be typically, it will be continuous with 0 t. I am going only to capital T because my external velocity field exists until time capital T, so that I am prevented to study the long time behavior. So in L1 of R2, intersection with continuous from 0 capital T with L infinity of R. For instance, in a space like that, you can show by a fixed point argument that you have a unique solution in such a space with appropriate norms that you can put. So for the, I mean, this is typically due to Fujita and Kato in the 60s. In the particular case of the vorticity equation, there is a paper by Lennart C, which gives the details in 1993. And you know that you have a unique solution, which can be done global, which depends continuously on the initial data and things like that. So if you have initial data which are in L1, you can solve this equation without any trouble, and you have a solution. The solution is smooth for positive time because it's Navier-Stokes and so on. So I didn't give any proof, just let's take this for granted. Of course, we are considering vortices, so you have many vortices which are in L1, but if you want to start with point vortices, we have to go to measure, which is sort of the weak closure of L1. It has the same scaling, but it's a little bit larger. So this I shall discuss tomorrow. So tomorrow we shall see that we can also start with a Dirac mass, and this is the problem we shall consider. What I really want to do is to consider this equation with a given velocity field, start with a Dirac mass somewhere, and see if I can follow the position, if the viscosity is small, if I can follow the position of this vortex, if I can compute how it deforms due to interaction, if I recover all the results that I have mentioned here, and this is typically what I try to do. Okay, it's enough for today, people. Except if there are some other questions.
Yes, it's
We had quite a few. Right. We have to do some kind of foundation of the vortex being done next part, right? I've never seen that. For vortices which are widely separated, the leaking of circulation you can have from one vortex to the other is extremely weak. So they keep the same circulation to a very good approximation. But in the regime we cannot describe so far, like the merging interaction. This is a completely different story. So I discussed with people doing numerics because I wanted to know
can we write some kind of a collision kernel? You have two vortices with position x1, x2, circulation gamma 1, gamma 2, size S1, S2. They merge. We don't know how to describe. What do you write? What is the result of this collision? What is the circulation? What is the position? What is the size? And they say we are not able to answer this question. For instance, if two vortices merge, it's not clear that the circulation of the resulting vortex is the sum of the circulation, because you have this fragmentation that goes to infinity. So towards a kinetic equation that could be then used to describe the coarsening process of having less and less vortices would be very beautiful. But so far, I think we don't even know, and we don't have the information to write the minimal information on the collision kernel that would be necessary to even start thinking about such a protection. So I don't know if people have more information than me, but it's what I have in.
Okay. So, the questions we think
I mean, we all go. There's a group of people going
And it should be there at 25 sharp.
Yeah.
It's the only time when not before, not after.